Hey everybody, Mrs. Herman here. We are going to talk a little bit more about probability and get a little more detailed with some choices, and we're going to learn about tree diagrams today. So we spent a little bit of time understanding tree diagrams, but we're going to go a little more in depth today when you have dependent and independent events and some different choices. So it's pretty easy to make a tree diagram maybe when you have one event or even two simple events, but it depends whether they're independent or dependent. So we're going to focus first on independent events. So what I mean by independent events would be you make one choice and then the second choice is not affected by your first choice, okay? Or maybe you got marbles and you take a marble out and you replace it before you pick it again. That first pick is not going to affect the second pick because I put the marble back. Those are all independent events. Rolling dice, flipping coins, all of those things would be independent. So for this example, I checked out the Starbucks menu, and for some reason the mocha cookie crumble frappuccino sounded good. So there's lots more choices than just two of them, but I narrowed it down to two different choices that you'd have to make when ordering one of these frappuccinos. So the first choice you'd have to make is what size frappuccino you would want. So to do a tree diagram, I always make mine left to right, but you could also make them vertical if you wanted to. So the first choice I have to make, there are three of them. I have to choose whether I want a tall size, a grande size, or a venti size. Okay, so my first choice, tall, grande, venti. Based on that, I can then choose whether I want a mocha drizzle or a cookie topping on my frappuccino. So I have two choices once I make that. So I'm going to just put MD for mocha drizzle and CT for cookie topping. So I have to do that for each of these sizes because these are all my possibilities I could have when choosing my frappuccino. Okay, so this is laying out every single thing. I could choose a tall with the mocha drizzle or a tall with the cookie topping. I could choose a venti with the mocha drizzle. Okay. When you are listing these, you might see some tree diagrams where they've got decimals or fractions written on them. That's to help you calculate probability. I'm a big fan of those ones. So for example, in my first choice, if I would do tall, that was one out of three different size choices. So I could have a 1/3 chance of choosing tall, a 1/3 chance of choosing grande, and a 1 out of 3 chance of choosing a venti. From there, I then go to my two choices of mocha drizzle or cookie topping. And so those are only two choices, so I've got a 1 out of 2 chance on each of those. Okay, so I just listed a couple problems off to the side where we could read our tree diagram to help figure that out. So the first probability question I have is the probability of a tall frappuccino with cookie topping. So if I'm going to follow along this, I picked tall, so that was a 1 out of 3 chance. And I multiply those fractions together, okay? So I'm going to multiply 1/3 by the cookie topping, and that fraction was 1/2. When I do 1/3 times 1/2, I get 1/6. And that makes sense if you're going along here. There are 1, 2, 3, 4, 5, 6 different options, 6 different outcomes, and only one of those is a tall with a cookie topping, okay? The next one is the probability of any size drink. All I'm specifying is it has to have mocha drizzle. So if I look up here, I could have a mocha drizzle there, I could have a mocha drizzle there, and a mocha drizzle there. If you're using your fractions, this option, a tall mocha drizzle would be 1/6 because of 1/3 times 1/2. A grande with mocha drizzle would be 1/6 also, and a venti mocha drizzle would be 1/6. So 1/6 plus 1/6 plus 1/6 is going to end up being 3/6 or 1/2. So either way, you can get to that same answer of half of my outcomes are going to involve a mocha drizzle. The other half would involve the cookie topping. Last but not least, I wanted the probability that my choice is going to be a venti. So I don't care what the second choice is, I just want it to be a really big frappuccino. So if we look down here, okay, I've got a 1 out of 3 chance of having a venti. Okay, I don't even really need to look at the cookie topping or the mocha drizzle because all I care about is the first choice of the size. So I've got a 2/6 because either this one or this one are going to be a venti. Or if I simplify that, that's 1/3. I'm going to circle those answers. So there's a way to make a tree diagram based on choices and still calculate your probability based on that. I'm going to scroll down to another scenario that would be like flipping coins. So let's say I'm going to do 3 flips. So you can either have 3 different coins. So maybe I'll say 3 flips or 3 coins. Okay, so this could be like 1 coin, you flip it 3 different times. Or I've just got 3 different coins and I flip them all at the same time and I'm going to record what happens. So this is going to represent either the first coin or the first flip. So I could get a head or a tail. Then my second flip would be here. And third would be another head or tail. Head or tail, head or tail, and head or tail. All right, so now that I have the 3 different coins or the 3 different flips listed, we can also fill in those fractions or decimals. So I've got a 1 out of 2 chance to get a head or a tail. They're equally likely. On the second coin or the second flip, I again have a 1 out of 2 chance on all of these happening. And then here, because there's again only 2 options, I have a 1 out of 2 chance for each of these. And you just multiply the fractions following the path you're looking for. So for example, this first problem, when I have 1 coin, okay, so I'm only really going to pay attention to this first section right here. I want to know what's the probability I'm going to get a head on my first flip. Well, if I'm only looking right here, I can do a head or a tail. So I've got 2 options, 2 outcomes, and only one of them is my desired one. So it's a 1 out of 2 that I'm going to get a head on my first flip. On the second one, 2 coins. So now I'm going to pay attention to the first 2 parts of this. What's the probability I'm going to get at least 2 heads? So to follow that, okay, I get a head on my first one, so that's 1/2 times a head on my second one is another 1/2. 1/2 times 1/2 is 1/4. Oops. So I have a 1 out of 4 chance that I'm going to flip 2 heads in a row or get a head then a head. Okay, you could also follow that by seeing, I've got 1, 2, 3, 4 total outcomes and only one of those paths follows H, then the next H. Lastly, 3 coins or 3 flips. I want to know the probability of getting 3 tails in a row. So one way you can do that is, since I have my table or my diagram already filled out, I could count there's 1, 2, 3, 4, 5, 6, 7, 8 total outcomes, and only one of those goes tail, tail, tail. Or in other words, if I follow this path, let me make that bigger. Only one option takes me to tail, tail, and then tail. So that's 1/2 times 1/2 times 1/2. Which is going to get me to that 1/8. Okay, those are 2 examples of when we have independent events, meaning the first thing doesn't affect the second thing, which does not affect the third thing. But let's go ahead and do an example of a dependent event. And the tree diagram is made the same, but the fractional or decimal values are going to be a little bit different. So we're going to go ahead, and here's a bag of marbles. You can see that there's 10 marbles in the bag, 7 are red, and 3 are blue. So we're going to go ahead and we're going to pick 2 times. So 2 picks. You could do 3, you could do 4. Every pick is just going to make your tree diagram even bigger. So for the first pick, I could pick red or I could pick blue. Now, unlike before where they were equally likely, I look at that bag of marbles and those are not equally likely chances of picking red and blue. Red is a 7 out of 10 chance. And blue is going to be a 3 out of 10 chance. So I'm just going to list those on there. So I'm more likely to pick red than blue, but I'm still going to list them on my tree diagram. After I pick that, so this is where we really have to think. I am not replacing these. That's what this dependent means. Not replacing. And we talked about that the other week. Okay, so if I were to pick a red on my second pick, okay, I need to list my probability of picking a red and my probability of picking a blue. Well, if I picked a red on the first one and I don't put it back, I now only have 9 marbles left. And since there were 7, but I already picked one out, there's only 6. So now I only have 6 out of 9 chances of picking a red on the second pick. The blue chances, since I didn't pick a blue on the first pick, I still have 3 blues, but remember, I didn't put that red marble back, so I still only have 9. So there's where my fractions come into play for that. Now if you were to do this, we're blue. So let's go back, put all the marbles back in, and let's assume on my first pick, I picked a blue. Okay, again, I've got 1, 2, 3 blue marbles with 10 total. I put the blue marble somewhere else, and now I pick again. I could pick a red or I could pick a blue. If I picked a blue marble to begin with, I know I only have 9 marbles left. But since I'm picking red, I still have 7 of those 9 marbles are going to be red. Okay, that's where that fraction comes from. Again, I pick a blue marble. I had a 3 out of 10 chance. Okay, I do not put that marble back. So I have 9 marbles in there. But blue marbles, there's 3 of them in the bag. And remember, I already picked one right here. So only 2 of them are left. So my fraction of picking a blue then another blue, okay, is going to be 2 out of 9. So now I can start calculating picking a red. So this first problem, pick the probability of picking a red. So that means any red, whether I pick a red here or I pick a red here. Meaning, and I like to highlight these paths, I could follow this path. Okay, so that would be like doing 7/10 times 6/9. I'm going to simplify that fraction to make our lives a lot easier. So 2/3. So that's 14/30. I could also pick a red and then a blue. That's still involving a red. So that would be like 7/10 times 1/3, which is that 3/9. That's 7/30. And then I still could pick a red if I did blue and then red. Didn't say it had to come first. So that again, now that's 3/10 on blue first, and then I follow the 7/9. So this is going to be 21/90. So I'm going to go ahead and make these out of 90 because I'm going to add all of these together. So let's see, times 3 times 3, what does that give me? 42, 21, and 21/90. So if I add all those up, so what, that's 42 and 42. My probability of getting a red is going to be 84/90. And you can simplify that from there. Then I'm going to go ahead and let me erase these highlighted marks. So let's hope that, let's make that small, so we don't get confused on the next problem. Okay, so that was like the most complicated one. The next one I want to know is what's the probability of picking a red then a blue? So if I highlight that path of picking a red then a blue, that is the only path that follows that scenario. So my red path is 7/10, my blue path is 3/9. So I'm going to do 7/10 times 3/9, and that's going to give me 21/90, and you could simplify from there. Lastly, what's the probability, again, let me erase this, of picking a blue and then another blue? So if I pick blue first, I follow this path, and then I pick blue second, I follow that path. So you might think, oh, that's like doing the red and the blue, but remember, they have different probabilities because there's more reds than blues in there. So I follow those fractions. This is where those fractions really help out. 3/10 for that blue, and then 2/9 for that blue. So 3/10 times 2/9 is, I only have a 6 out of 90 chance, and you can simplify that fraction of getting a blue then another blue. So which makes sense when you look up at that bag of marbles. So that's how you find, using tree diagrams, probability of dependent events. go ahead and reach out if you guys have any questions. Okay, but great job today,